Some fractals are made by repeating simple shapes, but this construction asks what happens when the repeated building block is not a line or a flat loop, but a knotted curve in three-dimensional space. The main idea is to combine a rule for repetition, a rule for movement and shrinking, and a knotted starting shape so that the final object has both fractal structure and knot structure. The explanation begins with the repeating pattern itself, then connects that pattern to a one-way state rule, a trefoil knot, and finally a single system that ties all three parts together. A self-similar object is one whose smaller parts resemble the whole, so a fractal can be built by repeatedly copying, shrinking, rotating, and placing pieces according to fixed rules. Classic examples often start with simple pieces such as a line segment or a triangle, and the same kind of copying rule is applied again and again to create detail at many scales. In this construction, the repeated pieces are organized into three size levels: a large-scale arrangement that sets the main shape, a middle-scale recursion that fills in the structure, and a small-scale twisting level that controls fine local detail. Each level uses transformations, meaning rules that take a shape in space and produce a smaller moved copy by combining shrinking, rotation, and translation. The shrinking part makes the pieces fit inside a bounded region. The rotation part turns each copy into the needed orientation, and the translation part moves the copy to its assigned position in three-dimensional space. The construction also uses three states, which can be thought of as three types of positions or stages that a piece may occupy during the recursive process. A Markov transition rule is a rule in which the next state depends only on the current state, not on the full history of how the object arrived there. The transition information can be stored in a 3x3 table, where each entry says whether a copy is allowed to move from one state to another. If the table allows a move from state 1 to state 2 but does not allow the reverse move from state 2 to state 1, then the rule has a built-in direction. That lack of balance is called asymmetry, and it makes the recursive paths favor some sequences of states over others instead of treating all directions equally. Because the allowed state changes keep pushing the construction along particular routes, the rule acts like a pump that drives the growth pattern through the three-state system. The geometric transformations turn this state rule into actual copies in space, so every allowed transition is matched with a shrinking, rotating, and shifting motion. The topological part of the construction comes from the trefoil knot, which is the simplest non-trivial knot and cannot be untangled into a plane circle without cutting it. A trefoil can be described as a curve that winds around a donut-shaped surface in two directions at once, producing a knot with three crossings in its usual diagram. Unlike a simple loop, a trefoil has chirality, which means it has a handedness like a left hand and a right hand, so its mirror image is not the same knot by ordinary bending. Using a trefoil as the basic seed gives each repeated loop a real knot structure, so the small copies are not merely curved decorations but knotted pieces with their own topological identity. For the final object to remain a connected continuum, the copied trefoils must be placed so that their attachments meet correctly, or else they must be kept separated without accidental intersections. A continuum is a connected, unbroken set, so the construction must control the placements carefully if it is meant to form one linked whole rather than a scattered dust of pieces. All of these rules fit into a graph-directed iterated function system, which is a fractal building system where a directed graph says which kinds of pieces may produce which other kinds of pieces. In this graph, the three states are the nodes, the allowed Markov transitions are the arrows, and the transformation attached to each arrow tells how to place the next smaller copy. Each state produces a component of the final set by collecting the transformed copies allowed by the arrows leaving that state together with its starting trefoil seed. The total fractal continuum is the union of the three state components, so the final shape comes from the combined behavior of the state graph, the spatial transformations, and the trefoil base knot. Because the transition rule is asymmetric, the limit object has a preferred structural direction, with some chains of trefoil copies appearing more naturally than their reversed chains. The result is a self-similar knotted continuum. Locally, it carries the trefoils, knotted crossings, and handedness, while globally it follows a three-tier Markov-driven fractal pattern.